In this video, I will go through the second effect of the torsion, which is the angle of twist, phi. So the angle through which a radial section of a body deflects from its normal position when the body is subjected to a torque. I would like to explain it in more details here. Keep in your mind, originally we have this shaft, which is fixed from this end. Fixed means no change in any position at this section. The only change that will happen due to the applied torque, maybe here or there or here, whatever. So I believe we will have this point will rotate to this new position due to the twisting of this member. But keep in your mind, this free end will twist, but this fixed end will not. So this point will remain as it is. Keep in your mind, if you make the line between this point and this point, and then between the same point at the fixed end and the new position of the point here, we will have angle, which is called phi, angle of twist. That makes sense? So keep in your mind, to get an angle of twist, this is a measurement between 2 points. So we have original line before twisting, and we have a new line after twisting. The angle in between, it is called angle of twist. That makes sense? How to figure out this angle of twist? Equal the applied torque T times the length of the member, capital L, divided by G, the polar moment of inertia, and G, the shear modulus of elasticity. Shear modulus of elasticity is a material property, and we covered this during the mechanical properties of material in the previous videos. So if we have only one element, one part with a length L and applied torque capital T, so the angle of twist equal TL divided by JG. But if we have different parts, many parts, or many values for the applied torque, I will say the final angle of twist equals summation TL divided by JG for each element or each segment. Does that make sense? So we have an example. We have a shaft with a diameter 20 millimeter, solid shaft subjected to the torques applied 80, 20, 30. We need to figure out the angle of twist at the end B, given the value of the G, shear modulus of elasticity, equals 7.5 times 10 to power 9. The first one, the value of J of this cross section with a diameter 20 millimeter equal pi divided by 32 times this diameter to power 4. So the value of J will be, where is the calculator? Here we go. So it will be pi, just a moment. So divided by 32 times 20 to power 4 will give you 15,700 millimeter to power 4. That makes sense? I will divide this shaft to 3 parts. Part BC, part CD, part DA. So let's start with the first part. Part BC. C. So to figure out the applied torque on this part, I'm gonna do cut. I'm gonna do cut. And then I'm gonna use the left part. So when you are doing this cut, here is your cut. And we have applied torque, looks like rotating clockwise, 80 Newton meter. This 80 Newton meter will give you the value of the torque at this cut, nothing else. This torque will be 80 Newton meter clockwise. If we assume clockwise is our positive value, so the counterclockwise will be the negative value. So I'm gonna assume this value will be positive. If you assumed something else, that's fine. The length of this part BC, equal 800 millimeter. Does that make sense? So I am done with part BC. I have the torque, I have the length, I have the value of J, 15,700. I know what will be the value of G, which is 7.5 times 10 to power 9. So I have everything related to part BC. I will do the same for part CD. I will do another cut in part CD. And I'm gonna use the left part because I don't like to work with the reaction at A. I don't know how much is this reaction. I don't care about it. So I'm gonna do cut and use the left part. Here is the left part. We have this cut. Keep in your mind, we have a torque here rotating clockwise equal 80. We have another torque here rotating in opposite direction equal 20. So the final torque at the cut will be, because 80 and 20 in opposite direction, so it will be subtracted, 80 minus 20. And because 80 is clockwise, I assumed it positive. 20 is counterclockwise, I assumed it negative. So the final will be 60 Newton meter will be positive because in the same direction of the assumed clockwise rotation. For part DA, so I'm gonna do another cut in part DA and I'm gonna use the left part. So here is your cut. We have a torque here clockwise, which is positive 80. We have here counterclockwise, which is negative 20. We have another one here. This one is rotating clockwise 30. So the final torque at your cut will be 80 plus 30 minus 20. It will be 90. That makes sense? So 80 plus 30 minus 20. Yes, it will be 90. So the length, I forgot to mention this, the length of part CD equal 600 millimeter. The length of part DA equal 200 millimeter. We are looking for the angle of twist at the free end B. Keep in your mind, the angle of twist phi will equal summation torque time L divided by J times G for each part. So it will be T times L divided by J, G for the first part, plus T times L divided by J times G for the second part, plus T times L divided by J times G for the third part. The first part B, C, the second one C, D, the third one D, A. Does that make sense? Go ahead and put your numbers. The torque on the first part, 80. The length of the first part was 800. The G for the first part and the second part and the third part the same, 15,700. And the value of G for all of them because the same material, 7.5 times 10 to power 9. This is for part number 1. Plus the torque on part number 2 will be 60. The length of part number 2 is 600. G 15,700. G 7.5 times 10 to power 9. Plus the third one, this is phi at the free end B. Yes. Plus the torque on the third part was 90, positive 90 in the same direction, which is clockwise. The length is 200 divided by 15,700 times 7.5 times 10 to power 9. Keep in your mind, this 80 is positive, this 60 is positive, this 90 is positive because all of them, the final result for each torque at each cut is clockwise based on your assumption. Does that make sense? This G is Newton per millimeter square. Is it correct? Is it megapascal? Yes, megapascal. So each one of these are Newton per millimeter square. This one in millimeter to power 4. This one in millimeter. So looks good. So far, so good. But this 80 is Newton meter. You go back to the applied torque, it's in Newton meter. So we have a mistake right now because everything in millimeter and Newton. So this one must be multiplied by 1,000 to be in Newton millimeter. Time 1,000 to be in Newton and millimeter. So I can say one time 10 to power negative 6 radian. This is the value clockwise rotation. This is the angle of twist at the free end B equal 1 times 10 to power negative 6. It's very important to divide your shaft to different parts because each part will have different lengths and a different torque. This is the reason why I divided this shaft to 3 parts. In the second example, we have another example, another shaft under the effect of applied torque equal 50 pound-foot, only one torque. However, the shaft will be divided to 2 parts, CB and PA. Why? Because we have 2 different cross sections. Part CB is a hollow shaft or tubular shaft BC, and the part BA or AB is a solid shaft. This is the reason why I'm going to divide this shaft to 2 parts. Part number 1, part BC. Part number 2 is part AB. Keep in your mind, for part BC, we have a hollow shaft with inner diameter, inner radius 0.5 and the outer radius equal 1 inch. For the part AB, we have a solid shaft with a radius equal 1 inch. That makes sense. The length of part BC equal 2 feet. The length of part BA or AB equal 3 feet. So I can figure out the value of J here equal by divided by 2 times the outer radius to power 4 minus the inner radius to power 4. So the value of J will be 1 minus 0.5 to power 4 times by divided by 2. It will be 1.47 inch to power 4. The J value here will be pi divided by 2 times this radius to power 4. It will be 1.57 inch to power 4. What else? The applied torque, since we have only one torque on this shaft, it will be constant on both the two parts. So the applied torque will be 50 pound-foot, and the applied torque here will equal 50 pound-foot. No need to do any cut, because if you do cut here and use the left part, will give you 50. If you did another cut here in the second part and you take the left part, it will give you also 50 pound per foot, 50 pound-foot, because we have only one torque applied on this shaft. So I can say the angle of twist at the free end C will equal summation T times L divided by J times G, which equal T for the first part 50, L of the first part 2 feet, divided by J of the first part 1.47, times G for the same material for the two parts 11 times 10 to power 6. This is for part BC, plus 50 times the length of the second part 3 feet, divided by J, which is 1.57, times G 11 times 10 to power 6. Before figuring out the final value, I would like to make sure the units are good. The units for the torsion is pound-foot. The length here is foot. The moment of inertia is inch to power 4. This G is PSI, which is pound per inch square. We have a mistake here. Pound is good, but the numerator in foot and the denominator in inch. So I'm gonna multiply this 50 by 12 and this 2 by 12. This 50 by 12 and this 3 by 12 to convert it to inch and pound inch. Then I can figure out the final rotation. It will be 12 times 50 times 2 times 12 divided by 1.47 times 11 times 10 to power 6 plus 12 times 50 times 3 times 12 divided by 1.57 times 11 times 10 to power 6. So the final value will be 2.14 times 10 to power negative 3 radian. This is the angle of twist at the free end C. That makes sense? This is the angle of twist at the free end C, equal 2.14 times 10 to power negative 3 radian in the same direction of this applied torque, which is clockwise. This is the angle of twist. If you are looking to figure out the shear stress, you can find out the shear stress tau equal T times C divided by G. You have the value of T, the value of the radius of the cross section, the value of G. You can figure out the shear stress in part BC. The shear stress in part AB will be the same, T times C divided by G. You have everything you need. Then the maximum one, or the maximum shear stress, will be the biggest one of the two values. I can repeat it for you. So I can say for shear stress, The shear stress in part B C equal the applied torque in this part 50 times the radius of this part 1 feet. I'm sorry, 1 inch. The radius is 1 inch divided by J 1.47. We need to adjust the units because this one is inch to power 4, this one in inch, this one is pound foot. So I will multiply it by 12 to be pound inch. Then I can figure out the stress. It will be 408.16 psi. This is the maximum shear stress in part BC. The maximum shear stress in part BA or AB will equal the applied torque 50 times the radius of this part 1 divided by 1.57, the value of the J, and the radius is 1 also. So the value of the shear stress, don't forget to multiply this 50 by 12. So 12 times 50 divided by 1.57 will give you a value 382.16 psi. So the maximum shear stress in this shaft in general will be the biggest value, 408.16 psi. We have one more example. For this shaft with a diameter 60 millimeter made from steel A36 subjected to the shown torques, we need to determine the angle of twist at the end A. So this shaft will be divided to different parts from A to B, from B to C. So part A, B. The length of this part, 600 millimeter. The value of J for this part, pi divided by 32 times this diameter 60 to power 4. The value of G for this part is 75 gigapascal. The applied torque on this part. To figure out the applied torque, I'm gonna do cut. Then I'm gonna use this part. So here is your cut. I did cut here. This applied torque is rotating clockwise 2 kilonewton meter. So I'm gonna assume positive is your clockwise. Anything else will be negative. So this rotation is clockwise, will be positive 2 kilonewton meter. This is for the first part. So pi divided by 32 times 60 to power 4, I got 1271700 millimeter to power 4. For the second part BC. What is the length of this part? The length equal 400 millimeter. What is the value of J? It will be 127,000. I'm sorry, 1,271,700 millimeter to power 4. The value of G equals the same value because we have the same material. What will be the value of the applied torque on this part? I'm gonna do cut, and I'm gonna use the right part because I don't like to work with the reaction at C. So here is your cut. We have applied torque here clockwise equal 2 kilonewton meter. We have another torque here rotating counterclockwise 3 kilonewton meter. So the clockwise will be positive 2 The counterclockwise will be -3, so the final value will be -1 kilonewton meter. Negative means rotating counterclockwise. That's fine. Keep each sign the same. So I can say the final angle of twist at the free end A will equal summation T times L divided by J times G for each part. For the first part AB, the applied torque was 2. The length of this part, 600. The value of J for this part, 1,271,000, I think 700, time the value of G, which is 75, plus part BC, the applied torque is -1. Why negative? Because it's rotating. The final result of the applied torque at this cut equal negative because it's rotating counterclockwise. So time the length of this part, which is 400. Just a moment. 400 divided by J, which is the same value, 1,271,700 times the same G, 75. We have a issue with the units, I believe. Keep in your mind, this one is kilonewton meter. Yes, kilonewton meter. This length in millimeter. This J in millimeter to power 4. This G in gigapascal. By the way, gigapascal is kilonewton per millimeter square. So this one is kilonewton, this one in kilonewton, that's fine. But each are in newton. So I have to multiply this one by 1,000 to be kilonewton millimeter. I have to multiply this one by 1,000 to be kilonewton millimeter. Then I can find out the angle of rotation. It will be positive 8.4 times 10 to power -3. Positive means clockwise rotation of the free end B. I'm sorry, the free end A. So please make sure what is the direction of the applied torque based on your assumption. I assumed the positive rotation of the torque is clockwise, so anything else will be negative because part AB will be under the effect of positive torque rotating clockwise. Part BC will be under the effect of -1 kilonewton meter counterclockwise. And I have to consider these signs when you are calculating the final rotation or the final angle of twist at the free end A. One more example in this video. We have this assembly, 2 shafts made from the same material. Each has a diameter of 1 inch. So keep in your mind, this shaft and this shaft will have the same diameter. That means the same value of J, which equal pi divided by 32 times this diameter to power 4. So the value will be pi divided by 32. It will be 0.098125 inch to power 4. So keep in your mind, they are supported by bearings. These 2 shafts are supported by bearings at A and B and C. These bearings are free rotation. So the bearing at A, the bearing at B, the bearing at C are free rotation, allow for free rotation. I can label this one A, B, C, D. This one is E, and this one is F. That makes sense? If support D is fixed, this one is fixed. And the shaft DE under the effect of 80 pound-foot, and the second shaft under the effect of this torque 40 pound-foot on this gear. We are looking to determine the angle of twist at the end B. What is the angle of twist here at B? So please pay more attention to this example. It's a little bit confused. So I will try to do my best to explain it in more details. I'm gonna start with the shaft AB. So we have a little gear here, and we have a bigger one here. And this is the shaft. This is end B, and this is end A. We are given applied torque rotating counterclockwise like this. How much? 40 pound-foot. I started with this one because we have free rotation at B. We have free rotation at A. So this torque will make the whole shaft to rotate clockwise. I'm sorry, to rotate counterclockwise with the same value or under the effect of the torque 40 pound-foot. So I can convert this torque to a force in this direction. And keep in your mind the radius of this gear equal 4 inch. So this torque is applied to the whole shaft. The whole shaft does not have any reaction because it's free to rotate. So I will convert this applied torque 40 to a force at the circumference of this gear. How can I do this? Just divide the applied torque by the radius of this gear. So the radius of this gear equal 4 inch. I'm gonna divide it by 12 to be converted to feet. It will be 0.33 feet. So if you divide 40 by 0.33, which is the radius in feet, then I can convert it to a force which equal 120 pound. That makes sense? Keep in your mind, the second shaft, we have another gear here connected to the shaft, which is connected at D as a fixed. And keep in your mind this shaft under the effect of a torque rotating clockwise, I'm sorry, counterclockwise, 80 pound-foot. Keep in your mind, we have a contact between this gear and this gear. So this applied force will apply another or the same force on the other gear at the connection point. This point and this point are connected here. So any force applied by this gear will be transmitted to the connected gear with the same value, 120 pounds. I will convert the transmitted force to a torque using this radius. The radius of this gear is given by 6 inch, which equivalent to 0.5 feet. If you multiply the applied force, I'm sorry, the transmitted force, 120 pound, times this radius 0.5 feet, I can convert it to a torque rotating clockwise. How much? 120 times 0.5 will equal 60 pound-foot. So the final conclusion, this is E. The final conclusion, I can say we have this shaft fixed at D, and this is E. We have here clockwise torque 60 pound-foot, and we have here counterclockwise 80 pound-foot. That makes sense? 60 and 80. The length of this shaft is 10 inch and 30 inch. 10 inch. 10 inch. Yes, 10 inch and 30 inch. That makes sense? And the G for this shaft equal 0.098 125 inch to power 4. I can tell you because this end D is fixed, so I can tell you what will be the phi, the angle of twist at the end E. We have two parts, first part and the second part. For part number 1, the length equal 10 inch, the J equal the same value 0.098125. The value of G, because we are using the same material, which equal to, it's not given, but I can assume it, 11 times 10 to power 6 psi. The value of the applied torque, I'm going to assume clockwise is my positive, counterclockwise is my negative. If you did cut here and used the right part, we have 80 counterclockwise negative. And we have 60 clockwise positive. Will give you negative 20 counterclockwise pound-foot. This is part number 1. For part number 2, the length of the second part number 2, is 30 inch. J 0.098125. G, the same material, 11 times 10 to power 6. What will be the value of the applied torque? So I am gonna do another cut in this part, and I'm gonna use the right part. The right part will give you only 60 pound-foot clockwise. Positive. That means the angle of twist at the free end E, or it's not the free, at the end E will equal summation T times L divided by J times G. For the first part, we have negative. What was the torque? 20. The length is 10 inch, J 0.098125, G 11 times 10 to power 6. Plus second part, the applied torque positive 60 times the length 30 inch divided by 0.98125 times 11 times 10 to power 6. Before calculating the final answer, make sure you have the correct units. This torque is given in pound-foot. This length in inch. This J in inch to power 4. This G is PSI, pound per inch square. So looks like everything looks good, but I have to multiply this torque by 12 to be in pound inch. Then I can find out the value, negative 20 times 12 times 10. So the value of the angle equal 0.01778 radian will rotate clockwise. So this gear at E will rotate clockwise. How much? Equal 0.01778 radian. Keep in your mind, this is a very good point. Since the two gears, the one at E is connected to the one at F, so this one is connected to a shaft and this one is connected to another shaft. So the angle of a twist at E, which equal 0.01778 radian, will be transmitted to another angle at F. Since the two gears are connected together and rotating together, how can I convert the angle of twist you calculated at E to another angle of twist at F? It's very simple. Just multiply phi at gear end E times the radius of the gear E will equal the angle of twist at the gear F times the radius of the gear F. So, one more time, this angle phi is the angle of twist of the shaft at the gear E. How can I convert it to another angle of twist for the second shaft at the gear F? Since the two gears are connected and rotating together, I can convert this angle of twist by this way. The angle of twist here times its radius equal the angle of twist here times the gear radius. So the phi at the gear E of the shaft at gear E equal 0.01778 times the radius of this shaft is 6 inch, I think, equal the unknown angle of twist at gear F times the radius of this shaft, which is 3 inch. Okay, this one, I'm sorry, this one is 4 and this one is 6. 4 and this one is 4. So the angle of twist of the shaft at gear F will equal 0.02667 radian. This is the angle of twist of the shaft AB at this point F. Does that make sense? Keep in your mind, this is the end B, this is the point F. Phi at F is known right now, 0.02667 radian. Since there is no torque between F and B, so I can say the angle of twist at B will equal the same angle of twist at F, equal 0.02667 radian. So the final conclusion, the angle of twist at the end B, which is required, will equal 0.02667 radian. Does that make sense? So this example is a more complicated example, but we covered a few concepts. The first concept, if we have applied torque, I can convert this torque to a force at the circumference of the gear. How? Divide the torque by the radius will be converted to a force. This force will be transmitted to the connected gear at E with the same value. Then this force divide time the radius of the second gear can be converted again to a torque. So this shaft under the effect of two torques, I can figure out the angle of twist at E. Once you get the angle of twist of the shaft at E, I can convert this angle of twist to another angle of twist to the connected gear. How? By this equation. The angle of twist at E times the radius of the gear here equal the angle of twist at F times the radius of this gear. Then I can figure out the angle of twist at F. Since between F and B, no torque is applied in between, so I can say the angle of twist at B will be the same like angle of twist at